Hi, it's Mr. Duffy. Welcome to chemistry. In today's lesson, we're going to be talking about nuclear reactions, and specifically, again, how to identify what type of nuclear reaction is going on. Now, we've talked about radioactivity, and we talked about some different scientists that were involved in this. Um, One of the first ones was Henry Becquerel. He was the person that discovered radioactivity, but Marie Curie and Pierre Curie, the Curies, were the ones that were able to describe what radioactivity actually was. Now, Ernest Rutherford is who we're going to talk about today, and he's the one that discovered different types of radioactivity. And so we're going to learn about the different types of radioactivity and um, how to show those nuclear reactions involving these different types. So, to remind you again, radioactivity, basically nuclear reactions, involve nuclei, the nucleus of an atom, which is unstable, and it gives off or decays down and gives off radioactive particles, and those again are radiation. So the general term for all these particles is just radiation. But specifically, again, there are different types of radiation. The first type of radiation we have here is called an alpha particle. And an alpha particle is a very large type of radiation. It's a helium nucleus. Basically, it's the most massive of the types of radiation. Um, two protons, two neutrons. Arguably, the most dangerous type of radiation is the gamma rays. Gamma rays are extremely high energy types of radiation. They're a type of energy. They're not a particle, but they again just carry a lot of energy in the form of electromagnetic radiation. Um, Visible light is a type of electromagnetic radiation, and ultraviolet light is what gives you a sunburn. And gamma rays are way worse than that. So they're even stronger than X-rays. Another type of radioactive particles are the proton, give off a proton, and give off a beta particle, which we call an electron, or a can give off a neutron. So let's talk about again, just again that nuclei are unstable and some terms here. Basically, radioactive decay is the spontaneous disintegration of a nucleus into lighter nucleus, accompanied by the emission of different particles, radiation, or both. Again, it gives off one of those different particles, or again, the gamma rays, or both at the same time. Nuclear radiation is the particles that's given off, and then the radioactive nuclide is the unstable nucleus that it came from. So let's talk more about those individual particles. The three most common really are the alpha particle, the beta particle, and the gamma radiation. Basically, again, alpha particle is the largest of those, and two protons, two neutrons. It's a helium nucleus, has a charge of a positive 2 because it again has two protons. A beta particle is really just another name for an electron, and again, when it's in the terms of radiation, then we call it a beta particle. Again, when it's going around the nucleus, we call it an electron. But when an electron is given off because of a nuclear reaction, we call it a beta particle. Again, it has a negative one charge because electrons have negative one charges. And then the final one here, we've got gamma radiation. And gamma radiation is not a particle itself. It's just, again, a type of high energy radiation. Um, and so, again, a very dangerous type of nuclear decay. And there are two other types. Basically, they're both electrons, but they happen a little differently in the nuclear reaction. One is called a positron, and basically it's an anti-electron. It still has the same mass as an electron, but it has a positive charge. It's a weird type of particle. And then another type of radioactivity is an electron capture. Instead of giving off an electron, it actually takes an electron and changes it into a neutron in the nucleus. So it takes an electron from the electron cloud and turns it into a neutron in the nucleus. It's kind of a weird type of nuclear reaction, but it again is a capture of an electron. Now, one of the columns that I didn't talk about in the last slides was the penetration ability. And basically, when we talk about radioactivity, I want to talk about like shielding yourself from it because it is dangerous. And depending on the type of radiation that you're going to be exposed to, determines again how dangerous that is. So alpha particles actually really are not that extremely dangerous. They can be blocked by a piece of paper, so they can't even go through a piece of paper. They would hit the piece of paper, and the paper would block it. Beta particles can go through the paper, but they can't go through like a block of wood. And really what's the most dangerous is the gamma particle. Gamma particles, again, go through pretty much everything. You need a very thick concrete wall to be able to stop a gamma particle. And when you're talking about a nuclear bomb, that's where a lot of the energy is coming from. Again, a lot of the energy is in these gamma rays, and you need a very thick bunker to be able to withstand the gamma rays being able to get into the bunker. So, anyways, that's the penetrating ability of different types of radiation. Now let's look at the different nuclear reactions. Again, there's 5 different nuclear reactions. Um, and here's the first one, an alpha particle being decayed down. So again, we have a large nucleus, it becomes a smaller nucleus and gives off an alpha particle. And so this is an example of radium-226. It transmutates by giving off alpha particle, alpha decay, and write the nuclear reaction that represents this process. Okay, so again, we have a large nucleus being broken down into a smaller nucleus and an alpha particle. Notice again, we're starting off with what it says in the problem, radium-226. I know it's radium-226 because the mass is right there, 226, and radium always has an atomic number of 88. If it gives off an alpha particle, this is the symbol for an alpha particle, or we can write it 42 helium, that's another way of saying it, then it basically becomes 2 protons less, so it becomes element number 86, which is radon, and then it also becomes 4 times less massive because 2 protons and 2 neutrons, so it becomes 226, it goes to 222. Now, when I write it this way on the bottom, I think that's the best way to kind of represent that that's alpha particle decay, alpha decay, is you can see the numbers on the top, they add up and they're the same. 226 on the left, 226 on the right, and again, the numbers on the bottom also add up. So 88 on the left and 88 on the right. Okay, so that's again, it has to add up to be the same on the top and the bottom. And that's true with a chemical reaction, which we haven't talked about, but it's also again true with nuclear reactions. The next type of reaction is a beta particle decay, and beta particles again are electrons, so it gives off an electron. This is an example of boron changing into carbon by beta decay. So boron 12 is 5 protons because it's boron, and it has a mass of 12, but that's unstable. It's unstable nucleus. And so again, to become stable, it gives off a beta particle, and doing that, it becomes carbon. It has now 6 protons. And again, the mass is still 12 because the mass of electron is 0. So if we look at, again, I think the best representation of that is in the bottom. Okay, if we look on the left, 12 on the left, the mass of 12, and a mass of 12 plus 0 on the right, so it's still 12. And on the bottom, we have a atomic number of 5. On the right side, we have 6 is now the atomic number of carbon, but the beta particle being given off has a charge of -1. So 6 plus -1 is still 5. So again, we need to kind of think of the bottom as charges and the top as masses, if we want to think of it that way. Okay? And that is a beta particle nuclear reaction. A gamma radiation nuclear reaction is basically, again, you're not changing the element itself. It's just giving off energy to become more stable. Gamma radiation normally does not give off come by itself. So if we're talking about a nuclear reaction, you're going to see an alpha particle, but also giving off gamma radiation. That's more common, or a beta particle giving off gamma radiation as well. So this is an example of a gamma radiation of a cobalt-60 nucleus, but again, not normally. You'd normally have alpha and a gamma radiation at the same time. So that's an equation for it. We have 2 more. So there are 2 more types of nuclear reactions. The next one we're going to talk about is what's called a positron emission. And a positron is basically an anti-electron. So it's an electron in mass, but it has a positive charge. So here, the example we're going to do is write a nuclear equation for the positron emission of potassium-38. Potassium-38, so potassium symbol is K, and it's element number 19 on the periodic table, and the mass in this problem, it says it's mass of 38. If it's going to give off a positron, that would be basically, again, a electron, and when it's in nuclear reaction, we use the letter beta, the Greek letter beta, so it's a 0 plus 1 charge. Basically, again, that leaves it basically is, again, what's left over. And so it has to be element 18, because 18 plus 1 would be element 19, which would add up to be what potassium is. And element 18 is argon, so we can kind of look that up. And again, on the top, a beta particle has 0 mass, so this argon would still have mass of 38. So this would be a beta positron emission of potassium 38. Our final type of nuclear reaction is an electron capture. Electron capture is a special type of radiation where the electron actually falls into the nucleus and becomes a neutron. Kind of weird, but that's what happens. So this one says, write the nuclear reaction for electron capture of silver 106. So silver is Ag. Now, one of the ways you can definitely tell it's electron capture is that it's going to be on the left side of the arrow. So this is actually the only one where the electron is on the left of the arrow. All the other reactions, nuclear reactions, are on the right side of the arrow because they're given off. This one is taken in. And so again, it takes in an electron, which would be 0, -1 charge. And again, it's going to turn that into a neutron. So it becomes, it's going to combine with a proton, become a neutron. And it's going to become element number 46, which is palladium, Pd. And that would still have a mass of 106. Okay, so these are the 5 types of nuclear reactions that we're going to be talking about in our class. Again, how to write them or identify them based on, again, their type. And hopefully this video was helpful. Thank you.